Okay, now these are the outputs coming out of the output layer at the end. And so we have two nodes and we have to compute the error for each of these two nodes. Node 6 stands for like. Node 7 stands for dislike. Okay. Node 6, the value of y, so here the y represents like. So it will be 1. And node 7 is for dislike, and this is a different y. Okay, there are two different nodes. Remember that we have the individual functions for all the different nodes. Node 7, the function is for dislike, so the y value is 1. Because this y stands for dislike. So it's like y sub dislike equal to 1. The first one, node 6 is y sub like. Okay. And the output that we have, that's our y hat. So this will be that and that. Okay. So we have y and y hat. Okay. And these are not like regression y and regression y hat. In regression analysis, error will be y minus y hat. That would be it. Okay. But that's not the case here. This is not like regression because we're using different weights for different nodes, and we're also converting the output into a sigmoid function. So there are some calculus involved here, and you go through all those calculations, which mercifully we won't go into. All right, so the error is this. So you go y hat, all right, so that's our y hat, times 1 minus y hat times y minus y hat. That is the error for node 6. Okay. And then copy that down, that would be the error for node 7. Now we need to take these two errors at node 6 and 7 and use those errors, okay, for revising all of these weights now, okay, in the backward pass. Okay, so in that process we use what is called a learning factor. So learning factor is usually between 0 and 1. Okay. Let's say that we're going to use, again, this is arbitrary. Okay. You may want to try different L values when you actually run SAS, okay, starting from a low L. Okay, if you use very low L, then the learning will be slow. Okay, it will take time. If you use large L, so you will make too many corrections, then you may miss the optimal solution. So it is not a straightforward thing like saying, okay, use low L or use high L. You have to fine tune. So that's the reason why this method sometimes is not preferred. Okay, there are different ways in which you can revise the weights in the neural network. This is a more straightforward one, but it is also problematic in the sense that we have to come up with a value of L which is kind of arbitrary. All right, so now we have the old weights for node 6, so which are these. Okay. Now error for node 6 is that. Okay, so that's the error for node 6. Well, we can set this up differently, I guess. So we need to find that L times error. So we could have probably done L times error right here and then done the weights. Okay, so these are this is the same error for node 6. All of these weights are for node 6, right? So the error is that, so you take the old weight, then add L, okay, absolute reference that, L times the error. So part of the error gets tacked onto the weight. So you're tweaking the weights using a portion of the error of that particular node. And you do the same thing here. 7, the old weights are here. Okay, and the error for node 7 is that. Okay, and then we can copy this formula down here, and that will give us the revised weights. Okay, let's put the border back. So these are the new weights for the arrows coming into 6 and 7, and also we have revised the bias for 6 and 7.